All right, this is the last part of our chapter 1820. Now, this is chapter 20 with circuits. As I've learned from the other ones, you can't see the video, but I did put the link in, so watch that and then come back here so we can go over it. So the first thing you want to do is watch how I set up the circuits, because the rest of this lecture won't really make sense if you don't do that. So pause, go look. So here's the ideas from the video. Right? So if I have a series circuit, so I have one path, right? So you can see that in this case, this is my positive side and this is my negative side, I think. Anyways, so my conventional current is going like this, right? So this is the top of my hill and this is the bottom of my hill if I'm looking at it. And so the battery pumps it back up, and then a little bit gets lost here, a little bit of the energy gets lost here, a little bit of the energy gets lost here, and then we pump it back up and we have all of our energy again. So the current goes from one resistor to another in series. There's only one path. The current has to be the same because we have conservation of current and charge, but the voltage splits. So that's the part you need to make sure you understand. So let's say we have 3 batteries, and those 3 batteries combined, let's just say, have 6 volts. If these are all identical light bulbs, then there'd be 2 volts of energy used there, 2 volts of energy used there, and 2 volts of energy there. So it'll be at the bottom of the hill, and it has to get pumped back up. Now, of course, if this light bulb, and we'll get into that, if that light bulb has a different amount of resistance, it might take more energy to get across, right? So it doesn't have to equally split. However, they do all have to add up, which is the equations, right? So my current stays the same, right? So I total equals I1 equals I2 equals I3, however many resistors or light bulbs, whatever you have. That's a sigma, right? That means the sum of all the individual currents. So I just add them up. So 2 plus 2 plus 2 was 6. And since we know Ohm's law, V equals IR, and so I can plug in IR total for V total and IR of individual I's for the VI, but then the I's cancel, I cancels, I cancels. And so you just end up with R total equals the sum of the R's. I mean, that seems really silly, I know, but think about it. It just means that you have more resistance. Common sense. Series circuits are easy. We like them. They're simple. So here's a check question. What happens to the resistance as you put more and more resistors? When you're in series, this is for series, remember, only for series, the resistance goes up, right? Because you have more to go through. So it's kind of like having to get over 3 bumps, right? Bump, bump, bump. Each one has resistance. And so I have to get over each of those. And I use up a little bit of energy each time. When we're in parallel, however, there's 2 paths. So now, and it's hard to tell my picture, but I think this is my positive side and this is my negative side. So my hill looks like that, right? And so, but the thing is, I only have 2 bumps at the same time, right? So it comes here and some goes that way and some goes that way. So there are 2 separate paths. So it splits between the resistors. So it moves in parallel. There are multiple paths. So I could have another path on another path. And they have the same voltage because they're both connected, right? That's connected to the battery. If that went away, I would still be connected to the battery. It doesn't make a difference. The voltage is not going to change across them. The energy is applying to them is both the same. But now the current splits. And because it has multiple paths, as we saw in the demo from FET, it's going to go faster. And so therefore, because you have less resistance, right? Because the resistance went down. It's like you have multiple paths. So instead of having one escape route, I have multiple escape routes, and I can go a lot faster than I could before. So the equations, again, very similar to our series 1, but this time instead of I total, we have V total is equal to V1, which is equal to V2, which is equal to V3, because they're all connected to the battery, as long as they're in parallel. And I total is now the sum of all the individual I's. So this time, though, we're substituting I equals V over R. So we end up with V over R is equal to V over R. One's total, one's individual. So the V's cancel. So you're left with 1 over R is equal to the sum of the 1 over Ri. So now my resistance is going down, right? Because when you add the reciprocals and take the reciprocal, the number gets less and less and less. So in parallel, the resistance goes down. That's interesting to note, like if you've ever been in your kitchen and I've done this before, I have my microwave going, my toaster oven going, my oven going, I keep adding more and more and more, and my resistance goes down, my current goes up, and lo and behold, I break my circuit breaker. I don't really break it, I pop my circuit breaker, because your circuit says, oh, too much current, going to cause a fire, problems, and it shuts everything down. So that's to save you, right? So it depends on how your kitchen is wired or whatever's wired. The reason why would you want to use a series circuit? Well, it's simple, right? You just connect one and the other. You saw in the video how hard it was for me just to connect 2 light bulbs. How many extra wires I need? Imagine 4 or 5 or 6 paths, right? But the nice thing about parallel is I don't have to have everything plugged in at the same time. When you're in a series circuit, right? So here's a series circuit. When I'm in a series circuit, if one of these things go out, there's no current. The current equals 0 because there's no path. There's no complete path. But if I'm in parallel, right, here's a parallel circuit, right? Now one of these goes out, current keeps going, yay! So I don't have to have my refrigerator, my oven, and my stove on all at the same time to make things go. Can you imagine you turned off your light and everything went out? That would be horrible. This one is also cheaper because you don't have as much current running. This one can cost more money because you have more going, but this one can cause fires. This one's a little safer. So there's a variety of reasons. Usually your house is wired in a combination of series and parallel because you just don't want to have everything in parallel and everything in series. So let's see if we can figure out how to figure out what's called the total or effective resistance for any of these things. And I know this one's really kind of hard to read, and I usually just make up my numbers anyways. But this is a series circuit, right? So you can see that there's a battery there, and then we have a resistor here, and a resistor here, and a resistor here. So let's say that's 1 ohm, 2 ohm, 3 ohm, and doesn't matter what the voltage is because I asked just for the total effective resistance. So this one, the RT, would be super easy. It's 1 plus 2. That is not a 1. I don't know what the heck that is. 1 plus 2 plus 3. We can do our math. That's 6. Nice and simple. Now notice this is 6, 6, 6. These are in parallel. I know. Don't make any comments. 6, 6, 6. So 6, 6, 6 means I do 1, 6 plus 1, 6 plus 1, 6, which is 3, 6, which is 1/2. But that is not the answer because you have to flip it over because that's equal to 1 over our total. And so that means our total is equal to 2. And I can't flip it. Oops, that's 2 ohms. Really, that says 2 ohms. So that is 2 ohms, right? So let's try the next one, 999. So it would be... this is getting too messy, so let's get rid of all that and do this next one. And so that would be 3/9, right? Because 1/9 plus 1/9 plus 1/9 is 3/9, which is 1/3. We get to play with fractions, isn't that fun? Which is 3, so this would be 3 ohms. And if we do the next one, we know that'd be 3/12. 3/12 is the same as 12 divided by 3 is 4. And so this would be 4 ohms. Notice though, 2, 3, 4 is less than 6, 9, 12 respectively, because as I add more, I end up with more, less resistance, and so the current is going up rather than if it was connected to the same potential difference with only one of those resistors. So let's see if we can make this a little more complicated. So now we want to figure out total resistances, total current, and I and V through each, right? So you're always looking at, do they want each or do they want total? So this is in parallel, which is nice, and that is a 9-volt battery. And I know it says kilo ohms, but let's just say it's ohms. So 10 ohms. I think that says 2 ohms, and that says 1 ohm. Well, that's what we're going to call it, whether it says it or not. So it's going to be 10, 2, and 1 ohms. So if I want to figure out V across 1, which is the same as V across 2, which is the same as V across 3, which is the same as V total, that would give me 9 volts. So everything has 9 volts. If I wanted to figure out the current through each path, that's super easy because we know I is equal to V over R. So that means I1 is equal to 9 divided by 10. So that's 0.9. And we know that that's I1. And then I2 would be equal to 9 divided by 2. Oh, goodness, I didn't bring out my calculator, which is 4.5. Obviously, these are all amps, right? And then, sorry, ran out of space, I3 would be equal to 9 divided by 1, which is 9 amps. So if I wanted the total current, I would just add them up. So 0.9 plus 4.5 is what, 5.4? I hope I'm doing that right. It would be no, because it'd be 5.5, no, 5.4, yeah, 5.4, and then 5.4 plus 9 would be 13.4 amps. Now, I also could have figured out the total, well, let's figure out the total resistance two different ways. So my total resistance should be V over R, so it would be 9 over the total, which is 13.4. So if I plug that in my calculator, that comes out to be 0.67 ohms. But I could have also just done 1 over 10 plus 1 over 2 plus 1 over 1, plug in my calculator, 10x to the negative 1 plus 2x to the negative 1 plus 1. And then, of course, I need to do 1 over that, so x to the negative 1. And mine's doing it in fractions, wouldn't you know? Let's see if I do that. Nope. Which, if I do 1 over it, so it comes out to be, well, it doesn't equal, but it's 5/8, which is the same as 0.62. Well, you know, it's close. We'll call it rounding, right? 0.67, 0.6. Anyways, you got the idea, right? You need to pay attention to whether it's asking for individual or for total. Okay, so let me erase this entire mess. Let's see if I do that. Will that erase everything? No. Okay, fine. What if I do that? No. Let's erase as best I can. All right, so now let's look at the next one. So the next one says that now we have a combination circuit. Oh my goodness. And so we can see where the current splits and where it's the same. So we look at this and I think that says 30 volts, but that's what we're going to pretend it says. And then these are so tiny. We're going to call this 10 ohms. And let's just make it easy. Let's make this 5 ohms, and let's make this 20 ohms, and we'll make this 30 ohms. Okay, so now we've got a whole bunch of craziness, right? So we know the current is going to split in the opposite ratio of the R's. What? Remember, current wants to go through the path of least resistance. So when I have all of my current coming out here, so I have I total coming out here, some's going to go this way and some's going to go that way. And you can see 10 to 5, this one is going to get 2 times the current as this one, right? So if I think of it as having 15 pieces of pie, is why I always like to look at it, then there's going to be a reverse split. So if we make it look like this so you can see it. All right, here's my 5 ohm and here's my 10 ohm. So if I know that 10/15 of the total current is going to go this way, and I know that 5/15 of the total current is going to go this way, so when I add that together, I get 15 out of 15 of the total current, right? But we know 10/15 is the same as 2/3, and 5/15 is the same as 1/3. So that means 1/3 of the current total is going this way, and 2/3 of the total current is going that way. Okay, so that's the concept, but we still haven't figured out what the total current is, right? So we got to do that. So we see that this is in parallel and this is in parallel, and they were series with each other. So let's do the math. So we've got 1/10 plus 1/5. Plug it in my calculator, and I've got 10 to the negative 1 plus 5 to the negative 1, and then I flip it over. It's 10/3, so 10 divided by 3. It's about 3.3. So 3.3 ohms for that first one. And the second set, right, the second set down here is 20. So 1 over 20 plus 1 over 30. So that's a 20, right? So 20 to the negative 1 plus 30 to the negative 1, and then take x to the negative 1. So that is going to be 12. So 12 plus 3.3 means I have 15.3 ohms for my total resistance, right? So my total current is going to be, we had 30, right? V over R, so it's going to be 30 divided by 15.3. So 30 divided by 15.3 would be 1.96. 1.96 amps. So that's my total current, right? So now, let's change colors. Let's do the individuals. So remember, I said for my 10 ohm one, so we'll call it I sub 10. I sub 10 would therefore be, what did we say? 1/3 of the total. So it'd be 1/3 of 1.96. So 1.96 times, oops, not times, right? Delete, divided by 3, so 0.65, so 0.65 amps, and I sub 5, that other one, would have 2/3 of the 1.96, so 2 times 1.96 divided by 3 comes out to be 1.3, give or take, we round. So it'd be 1.3 amps. And if I add those up, right, it should come out to be the 1.96. We can do the same thing for the 20 and the 30. It's getting a little messy in there. So how much goes through each one? So now let's do another color. So now we've got the current, and it's going through here and here. And so the 20 ohm is going to get, remember the total is 50, so it's going to get 30 over 50, which is 3/5 of the total current. And then the other one is going to get the reverse one, right? Because think of it, right? The 21 should get more current than the 31. And so then we go into the other side, and we end up with 20 over 50, which is 2/5 of the total current. We know my total current is 1.96. So that means we will multiply by 3/5, or we multiply by 2/5. And you could keep going, right? So hopefully that helps. You can try the last one as well if you would like. Then we have this thing called a fuse. A fuse is a device that just burns out when there's too much current, so you may have seen them. They look kind of like that. And I talked about that circuit breaker that flips. If you go outside to your house, too much current goes through, it flips, it turns off the circuit, you can turn it back on. So you should just understand what they are. This one has a little filament that just breaks, and so you have to put a new one in. You may have watched some TV shows where, the fuse broke, and they put in a coin because that conducts current. A little dangerous to do, though, right, to put a coin in there, because now it never burns out and you have too much current, you have a fire problem. Same thing with the circuit breaker. If the circuit breaker keeps popping, there's a problem, there's a short circuit, don't keep resetting it. That could be dangerous. Grounding is super important. They showed it a little bit in that one video. So grounding is the idea that you are touching the ground. So if I was like, here's my Vandy graph that I don't get to show you, and here I am standing. If I'm attached to the ground, right, then the electrons that here can go down through me, and I keep feeling shocks, right? If I wear like rubber-soled shoes or something like that, then I don't touch the ground. So you can ground things. They did that with induction, right? So if something is, like the balloon in the wall, so I put the balloon here, and then, so the positives stay here, remember, and then the negatives come here, and if I ground it, so I attach it to the ground, then those extra negatives can actually go through the ground. It's called grounding. So then when I move this away, you end up with extra positive charges because the negatives went away. It's that third prong in the plug, because these are going positive, negative, back and forth because it's AC, but it keeps it from building up a charge difference and causing a fire if you have a ground. So the earth is considered infinite neutral. You don't make it charged, and grounding is just super important. If you ever see a ground, current's not going through it because it just goes into the ground. Then the last thing in this chapter is something called Kirchhoff rules. You don't need to know a lot about it, but you should understand just the basic concept, which is the conservation of charge and the conservation of energy. And you can watch some more videos if you want to get more information. The basic idea is what I was just telling you before, is that if I have separate paths, right, for the current to go, conservation of charge just says that I have some current that's going to go this way and some current that's going to go this way. So this is I1, this is I2, right? And so when it comes back together, actually this would be a bad circuit, so let's put another resistor in there. It would be a short circuit because if there's no reason to go through the other one. But if we had it like this, right, then this would get all of the current, this would get only part of it, this would only get part of it, but if you add them together, you end up with I total. That's conservation of charge. Conservation of energy tells me that I only have a limited number of volts here, the voltage total, and some of it's going to make it go through this path, and some of it's going to make it go through that path. And so if I added up a loop, right, this loop of energy is always going to add up to what the total voltage is. This loop will also add up to 0 because there's nothing else pushing it to go forward. And that's about all you need to know. It's just really a concept. AP2, we hit that a little harder. But the basic, And then the last concept in the chapter is the idea of internal resistance. So a battery doesn't provide the voltage. So, you have a 9-volt battery, but it really is only providing maybe 8.9 volts. And that's because of this thing called internal resistance. So there's actually, to make the electrons flow through the battery, there is some sort of resistance that exists there. The total voltage is what it actually is creating. It's called EMF. Again, we'll talk more about that in AP2. It means electromotive force, but for now, it's just the total voltage. And so this is what it should have done, the 9 volts, minus the voltage taken up from the internal resistance, which gives you the voltage at the terminals of what you actually get. And that's it.